Okay, so I'm going to switch gears a little bit and be a little more philosophical and airy and vague, because it's very early. And then there'll be more data in the next couple of talks. So I want to talk really fairly generally about the atlasing or parcellation enterprise. We've clearly spent a lot of time and money over the last 20, 25 years doing this kind of work. And when I say atlasing, really I just mean any kind of effort to take some system or some structure and carve it up in various ways, right? So the idea is you have some, let's say the brain, and you want to carve it up into sections that seem, or it could be gradients, could be networks, but to carve it up into units in some sort of palatable sense that we can use for other purposes. And we spent a lot of time on this, and I think we all would like to believe that we're making progress, and I think we are. I mean, I think there's all kinds of very elegant, very powerful work that's come out over the last 20 or so years. We can ask how we would measure progress in principle or in practice, and I think in some sense many of us want to believe that what it means to have a better atlas of the human brain is to have something that progressively approximates reality more closely. In the same sense, I think we would say that for many other domains, right? I mean, what it is to do science better and better is to get a closer and closer approximation of the actual data-generating process, right? So whatever the complex set of processes is out in the world that generates the observations we see, we want models that approximate that more and more closely. Now, the interesting thing about this kind of work in particular is, almost by definition, right, we sort of insist on models that are fairly simple. I don't mean like simplistic, but we tend to want models that sort of fit in our heads. So when we talk about parcellations of individual brain regions like the insula or the striatum, you never see, or I don't think you very often see, 25 cluster solutions, right? We see sort of 3 to 4 cluster solutions because that seems like a good granularity given the size of the region. At the whole brain level, maybe 100, 200, but you don't see very many parcellations that are like 5,000 regions. Now that's kind of interesting, I think, because if you were to ask, like, how complex is the brain? Like, how many bits of information would you need to actually explain, even at a, let's say, at a cognitive neuroscience level, at a high level of abstraction, what the brain does? I'm guessing you would say probably more than 100 bits of information, right? You might need more than that. So it makes a lot of sense to talk about approximating reality. On the other hand, there is this very big gap between the complexity of the brain as we think it exists and the kinds of models that we use. And one example of that, I mean, there's lots of assumptions built into all the methods we use. One, I think, prominent example is for a very large class of clustering and parcellation methods, a lot of atlases, there is a sort of hard assignment assumption, right, which is that every voxel gets assigned to one cluster. Now that on its face is kind of a bizarre assumption, right? Like if you ask someone who studies the brain, do you think that the millions of neurons in this one little voxel that are organized in layers and columns and have connections that ramify and interdigitate could just be assigned to one box? Is that a plausible assumption? The answer is obviously not, right? It's a simplifying assumption because we would like to have sort of a neat prepackaged map that says, you know, here's a boundary between these two regions, they do something different. But on some level we know, right? I mean, and I've published papers that do this exact thing. We know this is a simplifying assumption, and the question is it too simplistic? And at what point would we say, well, maybe we should relax that assumption and allow probabilistic models or something more sophisticated? And I'm not implying that probabilistic models are better. Really, the point I want to make is reality is extremely complex. We are happy because we have certain cognitive capacity as humans with much, much simpler models, and so we have to sacrifice something. And you might say that you're going to sacrifice the probabilistic structure of the distribution of neurons in the brain. You might say, well, no, we're going to retain that, and we're going to impose spatial constraints, but you have to make some decision, right? We're not in a position to absorb very, very complex models. And so one thing that kind of sets us up for, I think, is this hopefully realization or acceptance that a lot of actually the kind of the way we evaluate our science and the way we determine whether an atlas is good or bad is fundamentally sort of a judgment call. I don't mean it's completely arbitrary. I just mean that you have to have certain goals and certain values, and everything you do after that is conditional on that, right? So if you're interested in cytoarchitectonics, the kinds of answers that are going to interest you are going to look very different from if you're interested in task fMRI. And it's not actually entirely clear that you need to care necessarily what people do, the other kind of work are actually producing. I'll come back to this in a second. But the general point is that we might want to be a little pragmatic about the way we think about these things. So it's not really the case that the answers we come up with are particularly good approximations of reality. They might be good given a certain purpose and accepting that we are ignoring a lot of complexity for the sake of doing, working in this particular niche. And if you think of some of the criteria that we use to evaluate sort of goodness or fitness for purpose, there's lots of them, right? And I'll talk about 3 and just highlight the fact that they all have sort of trade-offs. So one thing that you see very often is consistency or stability, right? We tend to want solutions that are stable, meaning if you fit the same kind of model or you try to construct the same kind of atlas in 2 different samples or 2 data sets, you're going to get roughly the same divisions. There's a lot of work increasingly, for example, a Glasser HCP atlas, right, that comes at this from the perspective of multimodality. Wouldn't it be nice if we have a single parcellation that spans multiple modalities so that you're sort of, the intuition is you're carving nature at similar joints, whether you're looking at architecture or task responses and so on. Now, that is, I think, a very compelling intuition, and I share it for the most part, but it's not, consistency is neither necessary nor sufficient, right? So for one thing, it's not necessary in the sense that if you don't have a huge amount of data, the true data generating model might not fit the data well, right? If you have a small amount of data, the complexity of your model is bounded by how much data you have. And so we're very often in a situation where we actually would not, even if someone handed you the truth in some sense, you would not be able to get it to fit the data well. You wouldn't actually be able to estimate, no, here's the actual boundary, even if you knew this was the kind of the right algorithmic approach to take. On the other hand, it's not sufficient because however complex and high dimensional the true data generating process is, there's going to be lots and lots of reductions of that structure that are highly stable, even though they may not be terribly interesting, right? And in a sense, when you do things like say, let's find the structure that is sort of most stable across modalities and people and contexts, you're actually looking for the most coarse-grained regularities, right? And you're almost by definition saying, well, we're not going to be able to detect things that are only important in the task-affirmed modality, only important in this population. And so there's nothing wrong with sort of pulling back and saying, let's find the most coarse-grained statistical regularities. But again, that is, we are making a sacrifice. And so that's, again, it's a constraint that's worth keeping in mind, but it's a weak constraint and it's one constraint. And it's entirely plausible, I think, to have an atlas that some people think is wonderful and suitable for some purposes, that doesn't have great consistency, so long as it's constrained by other things, like it's the right algorithmic approach, or it meets some theoretical desiderata, and so on. Another kind of thing you can say very often is, well, look, the way we would determine whether an atlas is useful is based on predictive utility, right? So in some sense, the best atlas or a good atlas is one that allows us to make good predictions. So maybe we are doing out-of-sample classification of some disorder, schizophrenia, or depression, and so on. And we want the parcellation of the brain that gives us a low-dimensional solution that we can then use to produce the best out-of-sample prediction. Right? And that also is a very strong intuition. Again, I think that there's something fundamentally right about that. Right? We want, in some sense, if you're carving nature at its joints, then you would expect the units you end up with to be particularly useful for predicting other things about reality. However, one kind of issue there is, in general, if you have enough data, generally speaking, the best thing you can do is increase the complexity of your model, right? And so again, we run into this kind of wall where we sort of end up with a trade-off. Do we want atlases and parcellation schemes that are simple enough that we can look at them and say, well, that thing has 200 or 300 units, and I can sort of understand them, right? They're spatially sensible, I can map them onto psychology in some way, and that's great. That will typically incur some penalty given enough data in terms of prediction. And so if you think of something like UK Biobank, not at all clear that it would make sense, if your goal is fundamentally predictive, to use any kind of dimensionality reduction, or at least use these kinds of dimensionality reduction schemes, right? If you have enough data, probably the best thing you can do is just build a big predictive model with individual voxels, or feed it all into some deep neural network that's going to learn nonlinear representations from that you may not understand, but are probably going to be more useful. So again, there are trade-offs, right? And whether something is a good solution depends to a large degree, I think, on what your goal is. And if it's fundamentally predictive, then maybe the kinds of atlases we produce are actually not that useful, unless you're limited to a certain data set size. The last thing I'll mention, not an exhaustive catalog, of course, I'm just kind of bringing up examples of considerations, is aesthetic preference. So, to my mind, it seems clear that probably the single biggest factor in determining whether we like, this particular parcellation or that one is actually aesthetic preference, meaning, and I don't mean that like, the images on the page look nice. I mean, people care about different things for reasons that are not entirely clear, right? So, like, I don't care at all about site architecture. I don't think there's anything wrong, bad about it. It just doesn't particularly interest me. And so I'm never probably going to be terribly interested in a site architectonically guided parcellation scheme. Whereas if you show me one that's based on task fMRI, I'm much more likely to be interested, and there are people here for whom the opposite is true. It's good to be upfront about that, right? There's nothing wrong with saying in our papers and in our work, look, if you are not fundamentally interested in this kind of work, don't bother, right? This is not for you. There might be something that could inform what you're doing, but there's no privileged level in that sense, and it's perfectly fine, I think, to say, conditional on this being what you're interested in, here's a thing that you might find useful. The general point, really, that I'm trying to make here is that goals and values matter in science, right? We would like to think that there's sort of some objective formula, there's some consistency metric that tells you, this is the best parcellation at the moment, and it's the best approximation of reality we have. We should just use that one until the next increment. But I think we should try to be more subtle in that and ask, what is it exactly that we're trying to accomplish in this case? And often there will be reasons why we don't want to use the sort of the latest and putatively greatest atlas out there. So I'll end with just two practical prescriptions, and I think they're not, I don't think anything I've said is sort of terribly new or exciting. I just think they're reminders that are worth keeping in mind when we think about how we carve up the brain at different levels. One is kind of what I've said several times now, which is that remember, the brain is fundamentally complex, and we should not confuse the map to the territory. So it's very natural once we have some partition of the brain to think, that's it right now. So now we talk in terms of those units, and we talk about, the fourth region in this 250 cluster scheme does this, and so on. But I think it's good to keep in mind that in most cases, it's not that the data are fairly messy and noisy and there's some low-dimensional manifold hiding in there waiting to be found. However messy our data is, the true data generating process is almost certainly much, much higher dimensional and much, much messier. And so I think that's a good principle to keep in mind, if only because it kind of serves to remind you that whenever you opt for a low-dimensional solution, you're sacrificing something. And there's a big gap between what we have in our papers and the brain as it exists. And so it's good to be very explicit about those assumptions. And so this takes me to the second point I want to make, which is be explicit about those assumptions. I think it would be great if, in addition to sort of the implicit, obviously we tacitly tell people this is the kind of work I'm interested in, this is the motivating question. It would be almost a good thing if we had like an explicit goals and values section in papers where you say, look, these are the assumptions of my method. I'm assuming that every voxel can be assigned to a discrete cluster. I know that's in some sense sort of a crazy thing to do, but I'm okay with that. And here are some other assumptions that I'm not okay with people making, and so I'm going to be very careful about the estimation method I use and so on. I think it'd be very good to make those kinds of judgments and be explicit about it in paper so that other people can build on that, evaluate that as they see fit. And I think that would help a little bit in terms of pushing progress forward and not getting hung up on sort of, is this the best atlas? What about the one that comes after it? So I will stop there. Thank you for your time.